Hello everyone, welcome to a new lecture. In this video, we will discuss exponential smoothing methods for time series forecasting. So we will focus on two methods, the simple and the double exponential smooth. So in this session, we will go over first the simple exponential smoothing, which is used when our time series is stationary. Pretty much it's when it's constant. And the double exponential smoothing will be used when we have a trend, maybe the time series increasing or decreasing. We will go over some basic metrics to assess how good is our forecast. And of course, we will discuss cross-validation when we are working with time series. Okay, so the two methods, they don't go together. So we need to understand when we're going to use one or the other. That's like the first step. So in the case of the simple exponential smoothing, we will use it mainly when our time series is constant. So when our process is stationary. This is how it looks. So in this plot, this is the linear time series, right? You see observations. So there is some randomness. But if you look, it's not like increasing, decreasing, and it's not clear if there is like a pattern. You can not see if there are seasonalities here. So pretty much this looks more like a stationary time series. It's important to mention that when you're deciding which model to pick, it is always important to visualize our time series so we can make a decision. So in this case, again, we will use the simple exponential smoothing, or we can use it when our time series is stationary, like in the example. All right. So once we have assessed that our time series is stationary, so we can proceed with the simple exponential smoothing, which requires mainly the estimation of L, which is the level. Is the level, or it's like the constant component or the of the time series. So in order to find the level per period, you need, if you see here in the question, there is a parameter alpha, which is known as the smoothing parameter, and it will be between 0 and 1. Alpha is not going to be assumed. You can like find the optimal value of alpha that's going to minimize the error in your model. So the idea of alpha is to decide like how much weight you're going to give to the new observation. Remember, YT is like in regression models or even classification models, we use Y to refer to the observed data. In time series, also in some books they use ZT to refer to the real values, but it's the same idea. It's just the Y. It's the observed value, right? So if alpha is big, close to 1, that means that we're giving a lot of weight to the latest observation. Now, if it does not the case, if alpha is small, then we're giving more weight to previous observations, right? Now, maybe you're thinking, why this is called exponential? Right? Because when you look at the equation, it's just alpha times yt plus 1 minus alpha times lt minus 1. So it is exponential if we, this expression here, this term, the lt minus 1, we plug in the equation here, so it will be like this. So lt is equal to alpha yt, that's exactly the same as the previous one, plus 1 minus alpha. But now I'm going to make a change. So instead of lt minus 1, I'm going to like develop that expression. So that's going to be alpha yt minus 1 yt minus 1 plus 1 minus alpha times lt minus 2, right? So if you multiply this, now you see that there will be some, like alpha square, 1 minus alpha square. And if you give, like, kind of like plugging in here, instead of lt minus 1, I rewrite the expression as I just did with lt minus 1, then you will see, like the exponents are going to increase. So that's why this is exponential smooth. It's because it smooths the weight of previous observations, right? Depending on the value of alpha. All right. So this is how it looks if you pick a small value or a large value for alpha. So if it's close to zero, then you give importance to previous observations. That's why you see that here the model is not changing like very abruptly based on the observations. It tries to capture the pattern. But when you have time series that are more, like a noisy, then maybe and you use alpha close to 1, so it's going to move based on the previous observation. So you will see more variability in your model. Okay, so how are we going to assess the error? So errors or residuals are the same. It's just as in regression models. The difference or the distance between the real value minus the forecast. That's it. Real value minus the prediction. That's our residual. This is just for a single period. Now you can compute the sum of squares of the errors. So you take each residual to the power of 2 and the sum of that. You can find the average and you get the mean square error. The problem with these two, these are very popular metrics, but the problem is that the units, they are square units, so they are difficult to, to make an interpretation. We want to minimize them, but again, it's difficult to make an interpretation. So typically, for interpretation purposes, and especially if you're presenting your results on a business context, you will use the MAPE, the mean absolute percentage error. So what you see here is like, this is the residual of the error divided by the real value. So this is just like an error measured as a percentage, right? And then you find the average. So ideally, we want this to be below 10%, below 5%, but I cannot generalize that. It will depend on the context, because depending on the context, then that will be considered a big number or as or a normal error. So again, the idea of these metrics, the sum of square, the mean square error, and the mapping is to get small errors. So we want to minimize them. We want to minimize them. So this is just a numerical example here for you to get an idea of the simple exponential smoothing. Once I cover the simple and the double, we will go to a Jupyter notebook and we will go over a couple of examples. Okay, so this is a simple problem. There are only 6 observations here, right? We're given alpha 0.3. So in order to make a prediction, let's say for period 6, because we have 5 periods, so future periods will be 6, 7, 8. Then in order to do so, we need to start estimating our level. So the first level typically is estimated at the first value that is given in your time series, right? So that's what the 100, or the other approach is just like you can find the average here. That's the one way to make an estimation. Okay, so then you start applying the level equation. So for the L2, the second period, the level, which is the constant component of the time series, is just the alpha value, 0.3, times the yt, the observed value, right? Plus 1 minus alpha, the 0.7, times yt minus 1. So this is L2, then the yt minus 1 will be y1, the observation of the real value at period equal to 1. So that's the 100 that you get here. So you keep applying the same equation, so you get the estimations. And the last estimation that you have here, L5, I'm saying the last is because you don't have more periods, you only have 5 periods here, is the one that you're going to use for predictions in future periods. So this is the equation for future values. The prediction is just the last level that you found. Since here, remember, in the simple exponential smoothing, we assume that the time series is constant. Therefore, the prediction is going to be a constant value. So if someone asks me, okay, what is the y hat for period 6, then that will be just the last level that we found, which is 103.51. If you want to predict period 7, it will be the same value in this case because it's a constant. It's a constant. That's not the same case for the double exponential smoothing that we will discuss shortly. So, okay? So you can compute the residuals because it's important to measure the mapping. So here, for period 2, is going to be equal to the observed value, the 108, and here the fitted value is going to be the level from the previous period. This is the equation. The current YT minus the level from the previous period. So for E2, we use L1, right? For E3, we use L2. So that's how you get the residuals. Once you have computed the residuals, you can get the sum square of the errors. So you need to square those residuals and then sum them. You can then find the average. And then if you measure the percentage of the error, right, that absolute percentage of those errors, then and you find the average, that's the MAPE value. So it's below 10%, ideally below 5%. So it's kind of like within the range. So this model is okay for this particular problem. All right. So not all time series are going to be stationary. Sometimes they are non-stationary, like in this specific example, where we see that if we take two different time intervals, like this one and this one, the average value here of the time series is different, right? There is a because it's increasing, there is a slope in our time series. Therefore, we cannot use the simple exponential smooth because it only has one element, which is the level. In order to capture this is when we use the double exponential smoothing or the Hall method. So in the Hall method, you have the level, which is the constant component of the time series, but also we need one more parameter to estimate the trend. And this is the uppercase T. It represents the trend. So it's going to be positive, negative. And since we're adding one more element into our model, we also need one more smoothing factor here. So remember that we had alpha for the level. We still have alpha for the level, but now we have beta for the trend. So the questions change because now the time series is increasing or decreasing. So for the level is alpha times yt, similar to the previous one, 1 minus alpha. But now instead of just using the level, we also add the trend because it's changing, right? It's changing. That's why we're adding this element here. Now, in the case of the trend, so we have beta times the difference between the levels to see the change, plus 1 minus beta times the previous estimation of the trend. Now, when you want to make a forecast of future values, so here H represents how many periods you want to forecast in advance. So let's say that, imagine that we have like 5 observations, like in the previous example, and you want to get a forecast for period 6. So H is equal to 1, right? It's like one more period. If you want period 7, sorry, H is going to be equal to 2. So how do you estimate those future values? With the last estimation of the level plus H times the trend. So if you want to estimate one future, like one period in advance, then that would be the last level that was estimated times the last trend that was estimated times 1. So H is going to be equal to 1. We will come back to this equation once we're solving a problem with numbers, like this one. So we have here six values, right? From 50 to 65. You can see here that is increasing, right? You can see it's like it begins in 50 and then goes up until 65. Remember that it's important to always visualize the time series. I'm not doing it because this is just like some small problem. We will do it once we get to the notebook to go over the two examples. All right, we have alpha and beta. So typically they won't be given. You need to find them. You need to find them. In Excel, you can find them using Solver, or if you're using R or Python, typically the packages that you use for time series, they will compute the optimal values of alpha and beta. They will just find which value between 0 and 1 minimizes the error. Okay, so you need to compute, like using the equation for the level and also the equation for the trend. You need to compute the values for every single period. Once you're done, then you compute the residuals, same as we did. Please notice here a difference. In the simple exponential smoothing, it was just the difference between YT and the level. But here, like the estimation of the fitted value is not just the level, because we also have the trend. So it's like LT minus 1 plus the trend of the previous period. You can get the metrics, some square root errors, and the map as a percentage error. Okay. Before I go to the more complete examples, it is important to mention something. Same as we have done in regression analysis, classification analysis, remember that we don't train our models with the full data set. Typically, we split our data, we perform what we call cross-validation. This is important for generalization. So here we have like two options. One option is, imagine that this is your full data set. So let me just draw. This is like my complete data set. So one option is just, like split it into like, 80% and 20%, 70-30, right? You have done that before. Train your time series model with, let's say with 70% of the data and then test it here. So measure, map some square root error, mean square error, or, all possible metrics that you want to do, that you want to apply. That's one option. The problem with this one is that it's very sensitive to this point here. Like if you pick this one or you pick this one, maybe remember that real life is messy. So maybe if there is a change here, an important change in your data in the time series, if increases or drops, then it might affect the measurement, out of the sample in the test set. So a most robust cross-validation method is the expanding window. The key here is like when you're doing regression and classification, you just split your data randomly, right? And you try, of course, to kind of like ensure that the variables are represented in the same way in training and testing. But in the case of the time series, you cannot do that. We cannot just split randomly because in this data structure, the sequence matters, right? So we need to ensure that the sequence, we keep the same sequence in our data. So how does this work? So the idea is that instead of taking the whole data set initially, so you can just take one, like let's say I have here, we have 12 observations, right? 12 observations. So initially in the fall one, we're taking 7 observations for training, right? So you train the model. This is not just for exponential smoothing, for simple, although this applies, for from any time series method. So we have 7 periods here. We train the model and then we evaluate the performance in the next period that was not included in the training. Right? That this is observation number 7. Then, since this is an expanding window, for the second fall, we increase our training. Instead of 6, now we have 7 observations, right? We train the model with the 7 observations, and we evaluate in the 8th observation that we haven't used. And we keep doing the same, like adding one more observation to the training set and moving the test set or the observation that we use for the test set until we complete, all the observations, right? So here we have like one error here, one more here, one more here, one more here, one more here, and we can compute, like the same metrics, the map, the sum square of the errors, mean square error, and we evaluate how good is the model. So this one is a little bit more reliable because it's not dependent of a single breaking point, like as we did with the traditional cross validation. Okay, so let's go to examples. All right. So here, the libraries, I think you have used most of them before. Pandas, Matplotlib for visualization, Pandas for data manipulation, stat models. This is it's not like scikit-learn. Scikit-learn, it's like a more modern library. It's a faster library. But the nice thing about stat models is that it provides a lot of information. So tests, statistics, it checks some hypotheses. So it's a nice package in general for regression, classification, and time series. So from here, we're going to use the simple exponential smoothing and the and here you can get also the exponential smoothing method. All right. So for the first problem, the description is we are going to analyze the foot traffic for a retail chain. So we're going to analyze the behavior of the foot traffic weekly. So we're giving the data here and we split the data. We're giving 60 observations. So our train size will be 48 and the remaining will be test. That's if we do all, like the traditional split. So let's visualize the time series. So this is how it looks. So you see randomness, but there is not like a clear pattern. It's not increasing, it's just like moving around the 100 value. In a couple of weeks or maybe next week, we will cover how to like perform some statistical analysis to like confirm whether this is stationary or not. For now, we're using just a visual inspection of the time series. So this is the training, and the dashed line represents the test data. Okay, so yes, it looks like stationary. So using simple exponential smoothing makes sense. Okay, so we apply the simple exponential smoothing. You see here, this one, the simple exponential smoothing, right? We provide the data. This one, the white train here, right? And it will compute alpha. It will find the optimal value of alpha. So it says that is 0.24. So here you have the equation, same equation that we just presented in the slides. This is just for your reference. Okay, so in this table, I highly encourage you to go over the table in detail because it shows the real value of the time series. So for example, you have the 103.54, that's the real value. This is the LT estimation of the level at that period. And the y hat is like the fitted value, right, of that period. So please be aware that it's the previous level, right? The level estimated in the previous period. So if you check, for example, the fitted value for time 3 or week 3, it's the estimation of the level at period 2. So you have the errors or the residuals in the last column. So what is important is that the level that you compute at the end, the 102.64, is the one that you use to make a forecast in the next periods. Since this is a simple exponential smoothing, so the forecast for period 49 is going to be 102.64. The forecast for period 50 is going to be the same constant value. Again, that's not always. This is just because this is simple exponential smoothing. When we have the double or the whole method, you need to add the slope or the trend. All right. So here you have the predictions, the table, and of course, a constant value. That's expected, right? Because it's the simple exponential smoothing. So this is a comparison of the fitted values with the real values. And then here you have the dash lines, the test data, the real test data. And of course, the horizontal line is the prediction of the forecast. And it's a constant, and it's a horizontal line because this is a simple exponential smooth, right? It has only one parameter, which is the level. You can measure the errors. In this case, the mapping, it's 4.36%. This is just measured in the test set. So here I'm just using one split. We're splitting in two parts. We train with one with the training set and we evaluate in the test set. So this is the evaluation in the test set. In the next problem, in problem number 2, we will include also the other cross-validation method that I presented. All right. So you can analyze the impact of changing alpha. If you have alpha close to zero, then your fitted values won't change that much, the variability of the time series. But as it increases, it tends to be more responsive to latest changes. Okay, so this is the cross validation for expanding window. I will leave it for the next problem. Okay, so for the double exponential smoothing or the Holmes method, we have a different time series. So here, our variable is the monthly revenue. It's measured in millions of dollars for a customer electronics retailer. So first step, let's visualize the time series. So this is how it looks. This is how it looks. You can see a clear difference with our previous example because now there is a change. If you take two different intervals, you see that the values of the average values are not the same. They are changing. There is a trend here, right? Like there is a positive trend. It's increasing. There is a positive slope in this time series, right? We split the data. We have the training and the test. Okay. So now instead of applying the simple, we use the double. So we use the exponential smoothing. Please note that now we have the trend, where we have like an additive trend, which is a linear trend. There are other options of trends, not just the linear one. We will discuss them later. Okay, so with this function, the nice thing is that this method will also fit the simple, double, and even something that we will discuss in a future video, which is the Winters method. That's when you have seasonalities. So on top of the level, on top of the trend, you can also have seasonalities, which is not the case of this particular problem. Right? So we train our whole method or our double exponential smoothing, right? We get alpha, beta, right? It's 0.29 and 0.18. Again, these values were optimized to minimize the error. So with that information, we can get our table, with all the details of real values, the level estimation, but now we also have the train estimation and the y-hat. So you can see, and let's go over, for example, this one. At period number 4, the y-hat or the fitted value is 1.77. So how do you get that? It's just the previous level, the 1.6874, plus the previous trend, the 0.0891. So the sum of these two will give you this fitted value. So same idea for the other fitted values. And with this, you can get the residual or the error and compute the matrix. Now, if you want to make like prediction for future values, like period 29 or 30, so that prediction is going to be the last level that you estimated, this one at period 28, the 4.18, plus the last trend that you estimated, which is 0.11. So if it's just one period in the future, like period 29, it's just one period in the future, will be level plus one time the trend. But if you want to predict like two periods in the future, let's say you want to get the value for the period 30, week 30, period 30, that will be the level plus two times the trend, right? If you have 5 periods in the future, then that will be the level plus 5 times the trend. So keep that in mind because that's really important. And you can see the calculations here, right? So it's just h, the period, and you see the equation, the level plus h times the trend. Please note that the levels, they are like it's a constant value, it's the last that you found. Same thing with the trends, it's just the last value that you computed. The nice thing about the exponential smoothing method is like you know that the last value for the L and for T, they include the information of the whole time series. It includes information of the previous values. All right. So once you have your method, so you need to evaluate the method. Of course, here you can compare it if you want with the simple exponential smoothing. It doesn't make sense because there is a trend that is very clear. So of course, the double exponential smoothing is going to be better. That's very clear. So when you measure the errors here, you will see that for the whole method, the mapping it's 5.5%, which is better. You can see, the sensitivity analysis for beta, what happens when beta changes, and we also have the cross validation using both alternatives, like the classic or traditional approach or the expanding window. In the expanding window, so here we're using mean train 20. That means that we are using the first 20 observations. I think there are 28 in total. Let me see. Yeah, there are 28 in total, as far as I remember. Yeah, in the training there are 28 in total. Okay, so in this cross validation method, we're using training for the training, and then the next one, observation 21, will be used for testing. Then in the second iteration, we include 21 observations in training, and we evaluate performance in observation 22. So you keep rolling the window or expanding the window, because it's not rolling, it's expanding the window until you get to observation 27 and evaluate in observation 28. So here you get the results of the cross-validation for whole, right? And the map it's small, it's 1.96%. Right, so it's good. It's good. In general, it's better to use the expanding window as opposed to the traditional cross-validation method. Okay, so for method selection, it's always important to first visualize. So if it's stationary, you can try the simple exponential smoothing. If there is a trend without seasonalities, you can try the Holtz method. That includes also the trend, right? Remember always to visualize your data. And these are not the only methods that we're gonna cover. In our next video, we will see how to handle seasonalities. And then in the upcoming weeks, we will discuss alternative methods that go beyond the exponential smoothing techniques. All right? So that's everything for this video. I'll see you in the next lecture.